Welcome back to Introduction to Statistics, Section 7.1a, the properties of the normal distribution. Let's take a look at rolling a die again. There are 6 possibilities on a 6-sided die, 1, 2, 3, 4, 5, and 6, whether they are numbers or dots, and each of those outcomes is equally likely. Ignore that. All right. The probability of rolling whatever number. Pick a number. The probability of rolling one of those numbers, 1 through 6, is 1/6. And as you can see, it's equal all the way across. Okay? It's not very interesting, actually. So, as you notice here, each of these is discrete. Okay? You're only going to get one or the other. So this is a uniform probability and distribution, but those are discrete numbers. You're never going to get 4.5 if you roll a 6-sided die. Let's take a look at something that does not involve discrete numbers. Okay, so I'm going to ask you to use your imagination. I want you to imagine that you are an elementary school teacher and you have a bunch of 3rd graders and you're taking them to a museum. Okay? So in this museum, there is a video presentation about flatboats, and it runs on a loop every 12 minutes. But there's a little, break between when it starts. But the question is, how long can you keep those 3rd graders behaving? How long will it take them to start finding things to do they should not do? And I think it's, about 3 minutes. Okay, but here's the probability distribution first. And it looks like I lost my axes when I converted this PDF. Now the probability of that video starting, since it starts every 12 minutes, okay, within this 12 minutes of their arrival, that probability is marked over here. It's 1 out of 12 if you consider a 1 minute time frame, maybe this 1 minute. Okay, they arrive, class files in, takes them a minute to file in, and they are there and ready to go, and the video starts at that time. What's the probability? It's 1 out of 12. All right, or 0.083. So let's look at the probability that the video starts within 3 minutes of their arrival. So if this is A, then here's their arrival plus 3, and that's in minutes. Right, so we'd like to know what the probability is that it starts here, not just at a certain time, but within that first 3 minutes. As an aside, the conjugate of this would be the probability that it occurs in the last 9 minutes. Okay, but right now we're not looking at that. We're just looking at the first 3 minutes. So we can really look at this as an area problem because the probability here is 0.083 or 1/12. And that can be considered the length of this side. Whereas the width of this side measured in minutes is 3. So actually, the probability equals the area. Okay, the probability of it starting at a given minute is 0.083, and we have a 3-minute time span over which that could occur. So what we have here is 9, 24, 0. Well, go ahead and do the 0 or not. But 1, 2, 3, 0.249. So the probability of avoiding chaos on this school trip as it relates to this video is 0.249%. So you have a approximately 1 in 4 chance of this video going well for your class. Good, bad, might want to skip the video. Let me try to clean this up. There we go. That's the one I need. Sorry, my app is a little bit glitchy today, so I'm having to baby it. And clean all those up before I move on, or they will remain on the screen. And there's a reminder to take notes, because taking notes is always good. You can reorganize my babbling into a coherent format for yourself. Okay, so if the total area under the graph of an equation over all the possible values of the random variable equals 1, and that was our situation really. We had a 12-minute time span. If you remember, we had those 12 minutes. And each of those 12 minutes was equally likely. And so 1/12, 0.083, okay? Everything was equally likely, and this is 12, the area. 12 times 1/12. That area equals 1. And I apologize, I'm rushing to get this video out to you, so the quality isn't what I would like for it to be, especially since my app is acting up. So let's just see what we can do here. Clean this up a little bit. Maybe. There we go. That's cleaned up a bit. Okay, so here it is again. If the total area under the graph of an equation over all possible values of the random variable equals 1, and the height of the graph of the equation is greater than or equal to 0 for all values of the random variable. Okay, so there are no negative probabilities, so there's no negative height. There could be a 0 probability, but it has to be 0 or greater. So the height of the graph is greater than or equal to 0 for all values of the random variable. Okay, then the equation is a probability density function, and it is used to compute probabilities of continuous random variables. So that's why we took that little side trip into probability, because probability is definitely a part of statistics. All right. And PDF no longer just means a file that I send to you. It also now means a probability density function. So a PDF in this class, I'm going to have to deal with two definitions. The PDF refers to probability density function. It's used to compute probabilities of continuous random variables. So the probability density function that we were working with, okay, had a height, once again, of 0.083, a width of 12, and if we express this as 1/12 instead of 0.083, once again, it is very easy to see that the area within there is 1, and that whole area was a probability density function. So that was an instance of a continuous variable being equally likely, uniform. There's a uniform probability density function. Usually we are not going to work with those. And I'm sorry, it's acting up again. the probability density function that we will most often be working with should be familiar to you. It is the normal curve with your mean here. So either the mean of the population or the mean of the sample. Okay, so for now, I'm just going to go ahead and write that out here as the mean. Okay, if we're talking in generalities about the mean and the standard deviations, this is the way we usually refer to them, by the word mean and by plus or minus 1 standard deviation, 1 SD, 2 SD, 3 SD, which is why the term SD shows up in that rap that I gave you to remember the percentages involved in the empirical rule. So 1, 2, 3 standard deviations above the mean, 1, 2, 3 standard deviations below the mean. This is, in addition to being a normal curve, it can also represent a probability density function. Or PDF. Okay, let's see. Does this follow the rules for it being a probability density function? I believe I already told you that the area under this curve, the normal curve, is always considered to be 1. Okay, 100% of the outcomes for any trial will be shown under this normal curve. So the area is 1, and all of the probabilities are greater than 0 because this normal curve never touches, although it may appear to get very, very close, and it does get infinitely close, but it never touches this line, which represents 0. On the test, that 0 line did not make it through formatting and printing, but it should have been there. You should always have a bottom to your normal curves. Make sure you get that line in there. This is the most frequently used continuous probability density function. It will be very useful to you. So let's just move this out of the way for the moment. And I want to show you something. All right, here is a list of properties of the normal density curve that is straight from your book. And as we're talking about this, let me draw a normal density curve up here. Okay, the normal curve is symmetric about the mean, which is mu. We're going to be using population symbols here. Okay, because mean equals the median equals the mode, because this is a perfect normal density curve. It's a perfectly symmetrical curve. It has a single peak where x equals mu. Okay, x being the value of mu. The normal curve has inflection points at mu plus 1 standard deviation and mu minus 1 standard deviation. And what an inflection point is, it's where the curve goes from being concave down to concave up. And it occurs right at that point. Okay, even though my graph doesn't show it perfectly. Right, the area under the normal curve is 1, check. The area under the normal curve to the right of mu equals the area under the normal curve to the left of mu. Boy, that didn't show up either. Okay, everything is mirrored on the other side. Okay, and in each case, that equals 1/2. If the area under the whole curve is 1, the area of half of it is 1/2. And as x increases without bound, in other words, as x gets bigger and bigger and bigger, the curve itself approaches the horizontal axis. And on the left side, as x approaches negative infinity or gets smaller and smaller, more and more negative, really, the graph approaches but never reaches the horizontal axis. See you in part 2 of this video series.